Okay, welcome to today's lecture. So today we will analyze the second order rates for our noisy channel coding process. Okay, so let us first recall what we did in the last lecture, and we'll be visiting some of it again. So in the last lecture, we saw a proof of the achievability of the smooth hypothesis testing mutual information, I mean, for the one-shot noisy channel coding. And we saw an almost matching weak converse also. And then we went on to strong converse for noisy channel coding in the asymptotic IID setting. And the proof of the strong converse used techniques from the one-shot theorem. So the theorems that we showed were for one-shot achievability, consider a channel C mapping the input alphabet X to a probability distribution on the output alphabet Y, given by this. So the channel can be used exactly once. Then we showed that this rate, which is the smooth, smooth hypothesis testing.
There's a lot of noise in the background, screaming.
Yeah, that's.
Oh, is that okay? Yeah, sorry. Yeah.
So
Sorry.
there is this.
No, I got it. I understand.
Right.
Sorry.
So there is the smooth hypothesis testing mutual information, IF7 min, and we have to maximize it over all input probability distributions, PX. Okay. So that's the rate minus this fudge of log 1 by delta. So this rate is achievable with the error probability epsilon plus delta. So the epsilon is a smoothing parameter for I min, okay, and delta is this additive loss that you incur, and we can get the error probability epsilon plus delta. So this was shown by using the packing lemma. And then there was an almost matching converse, one-shot weak converse, which we proved, which states the following: that any coding strategy with error less than epsilon requires rate less than this quantity. So this quantity is again the smooth I min, okay, and I'm maximizing it over all input distributions PX. Okay. And then we also had a more refined weak converse, and from the refined weak converse we went on to the strong converse problem. So at the one-shot level, using the refined weak converse, we can make the following statement about the strong converse: that any coding strategy with rate R prime greater than this quantity. So what is this quantity? So it's the same hypothesis testing mutual information, okay? But the difference is, instead of py here in the mutual information, I have py, so px times py. So here I replace py by an arbitrary distribution qy. So px times qy. So as before, I have to maximize over the input probability distribution px, but to evaluate this, I'm going to minimize over all qy's. Okay, so this is the okay, so for the one-shot converse, I have to look at error of 1 minus epsilon. So one should have looked at d min of 1 minus epsilon, which is roughly d max of epsilon. So more precisely, we have to use this fudge terms of delta. Okay, so now we are going to analyze this quantity, so which is d max with smoothing error of epsilon minus delta of pxy, the joint pxy, with respect to px times py. Okay, so px is the marginal of p, qy is an arbitrary probability distributions, and we have that max min criteria. We maximize over input probability distributions, minimize over qy, arbitrary distributions on the output. Okay. So any coding strategy with rate greater than this quantity will give an error at least 1 minus epsilon. So we saw this, and then we started leveraging it to prove an asymptotic IID strong converse. So there were, there were some slightly difficult moments which we revisit today because they're crucial to understanding the strong converse as well as appreciating the second order rates. Okay. But the aim was to prove a strong converse for the asymptotic IID case, which finally says that any coding strategy with rate per channel use of greater than the mutual information, the Shannon mutual information maximized towards input distributions Px. So this is what is traditionally known as the channel capacity, the single letter expression for the channel capacity. So any coding strategy with the rate per channel use greater than the channel capacity will give error larger than 1 minus epsilon. And you note that epsilon does not appear in the channel capacity expression. So you can actually let epsilon go to 0. Okay. Of course, the theorem will be meaningful only for large enough n. So if you want to drive epsilon smaller, the theorem will be meaningful for even larger n, n being the number of channel repetitions. Okay, but any rate per channel use strictly greater than the capacity will, for large enough n, give error approaching 1. Okay, so that's the strong converse. Okay. So the setup for today is we are going to analyze the asymptotic behavior of so we are going to analyze the asymptotic behavior of the log likelihood ratio. Okay. So let's start slowly. So let Py and Qy be probability distributions on the same sample space Y. Define a random variable L. So L will map a symbol Y to the log likelihood ratio. Okay. So log of Py by Qy. And for this random variable, we are going to start computing moments. Okay. Now, the moments, to compute moments, we have to put up underlying probability distribution on these Ys. So the underlying probability distribution for calculating moments will be Py. In other words, the random variable is a function mapping the symbol Y to this real number. And then we are going to analyze the moments of the random variable when I put the distribution Py on Y. So
Pranav, this is just a small typo in the definition of relative entropy. It's summation over y's, not x's.
Or not x's, yeah. Right. Yeah. So remember that our divergences, relative entropies, and all the divergences are asymmetric quantities. P and Q are treated asymmetrically. So that is reflected in the fact that I'm going to consider the moments of random variable Y under the probability distribution Py only. Okay, not under any other probability distribution. So what is the relative entropy? It is nothing but the expectation of this random variable. So the Shannon relative entropy D is the expectation of this random variable when Y is given the probability distribution Py, which evaluates to this. Then we will define two more quantities which will be useful for analysis. The second one I'll call divergence variance. So the symbol for that is V of P with respect to Q. It is nothing but the variance of the random variable L under the underlying probability distribution, which we know evaluates to this. Okay, expectation of L square minus expectation of L whole square. Okay, so expectation of L I know is the relative entropy D of P with respect to Q whole square. And what is expectation of L square, the squared random variable? Just by definition, it's this. Yeah, so there should be again summation over 1. Okay. So this is an important quantity which we need. And the proof will also need a third moment of this random variable. So to make things very clear, I'm talking third absolute centralized moment of log likelihood. Okay. So I'm going to call it T of P with respect to Q. By definition, it is the expectation of the following quantities. Yeah. So take the random variable L. Centralizing it means you remove its expectation.
I just have a question. So this is kind of this is not the usual moment. This is the absolute because you're putting the mod. But normally, centralized
so
moment does not have the mod, right?
Correct. That's why I made things very clear. Third absolute centralized moment.
Oh, okay.
Of log likelihood. The random variable is log likelihood.
I want to be clear on something. So what are we exactly proving today? Are we proving that lemma that you had alluded to in the last class, that for a k block it's the D max quantity is exactly equal to the dpq plus some order of k small o of k terms. Are we proving that?
Yes, we are proving that.
Okay.
And we need these definitions to prove it. Okay. So yeah. So L is the log likelihood random variable. So we have to centralize it. That means remove its expectation. In other words, drive the expectation down to 0. So that's, I've done this out here. Then absolute means you have to put mods around it. Okay. And third moment is this. So you cube the resulting random variable and take its expectation under the good old underlying probability distribution. And just you expand things out, and this looks like this. Okay. So this is the random variable. This is where I'm removing its expectation, absolute values, and then it's take the mod cube and take the expectation under P1. Yeah. So
okay.
Yeah. Okay. So after defining this, let us analyze.
So I just have a quick question. So the point is that I mean now I'm starting to see one of the advantages of going to Dmax instead of working with Dmin, because Dmax we have this nice way of writing it as the like in terms of the likelihood ratio, right? But I mean Dmin also has a nice way in terms of the LP, but for this analysis I think it's much better to write it as a likelihood ratio and think of the likelihood ratio terms as random variables themselves, right?
Correct. Yeah. For this analysis, it's easier to work with a log like. So yeah, that happens. I mean, sometimes you want to prove something for Dmin, but it's simpler to work with DS. Okay, because DS is defined in terms of log like.
DS is terms of the log like. Right.
So you can repeat this argument with DS also. What I'm about to say, and essentially all the arguments you get. Yeah. So this I mean what you're seeing today is some proof on the log likelihood ratio. Okay?
Yeah.
Okay. So let's continue. Okay. So let's recall. Suppose I have a vector z. Okay. So this should be y again to correct this. So so this z is a mod y tuple. In other words, the coordinates of z are indexed by little y, where y ranges over the sample space capital Y. Now take any vector z. So its third LP norm, its LC norm, we all know what it means. But here we are taking slightly different definition of LP norm. We are taking the LP norm under the underlying probability distribution P. Okay. So the LP norm is you take the mod of the vector. Okay. So mod zy. So cube it and take the expectation of it under the probability distribution Py. Now, standard inequalities which can be found in textbooks, we show that this is actually a norm. By this I mean, of course, the norm of I mean this expression applied to the all zero vector is 0. If the vector is not all zero, then this expression is the non-zero, so strictly positive. Then if I multiply the vector z by a scalar, so the norm of alpha z is alpha times norm of z, and lastly it satisfies the triangle inequality. The L3 norm of z1 plus z2 is less than the norm of z1 plus norm of z2. So now let's go back to the third moment. So what was the third moment? Right. So it was the random variable L, then its expectation removed, mod taken, and then take the expectation under P. So the random variable is L. Its expectation, I'm writing D shorthand. D is the divergence. Remove the expectation and then take the L3 norm as defined out here. Okay. So, okay, this cube should not be there because I put a 1/3 out here. Okay, so the third moment raised to the power 1/3 is nothing but the L3 norm of L minus D. Now, in this expression,
Yeah,
L
the
is a
cube
vector.
should not be there.
Yeah. In this expression, L is a vector, right? So for each coordinate of Ly, I'm subtracting the expectation D. So in this expression, think of D also as a mod Y tuple, where every coordinate takes the same value, namely the relative entropy, the expectation. Okay? So the notation to be interpreted here is the all D vector. Okay? Now I can apply triangle inequality. So I get the 3 norm of L3 plus the 3 norm D. Okay, but I'll use the properties of the norm. So remember, this is the all D's vector. So pull the D out, and then I have to look at the 3 norm of the all ones vector. So the 3 norm of the all ones vector is 1. Remember, I'm taking an expectation. So I get this from there. And now I'm just writing the log likelihood ratio. So if you recall the expression, the log likelihood was log of Py by Qy, but I'm writing in this slightly fancy notation. Now I'm applying the triangle inequality to get this. Now this quantity I'll call T. Okay, in my later proof. This quantity
just to make things clear, so this minus log 1 over Py, these are all treated as vectors now, right? Y vectors. So
vectors these are all Y.
Y.
These are all Y.
Okay.
Yeah. Okay. So this quantity T, which is just defined here, is a property of Py and Qy. Property of the probability distribution. Now, what is interesting, for example, is that let us say I take the first distribution P to be a certain joint distribution on XY, and Q to be the tensor product of the margins, for example. Okay. Then one can show some nice upper bounds for T. One can show that one can show this expression. So let's see how. So let us say I'm trying to compute the 3 norm of this vector. Okay. So take the value at one particular coordinate. Let's say I call it X. Then or what I'm going to do, the contribution is log cube of 1 by X out here. Okay. And the probability distribution is and the probability there is X. So let us say X is Py out here, and then evaluate it. Okay. Then by simple calculus,
wait. So one second. So this your first is instantiating this Py to be P. Sorry.
Yeah. So for this inequality, treat X as Py.
Pxy, right? Pxy, because this Py. I see. P of
yeah. So
So
eventually it will become Px. Okay. Yeah. Sure.
Yeah.
So sure. Yeah. Actually, why not? Let's do that. That will be better in the long run. So the first distribution P, I'm taking Pxy. So the probability of a particular coordinate will be P of X comma Y. So treat this X as P of X comma Y. Okay? Times log cube 1 by P of X comma Y. So for X lying between 0 and 1, this is always less than this constant, which you can easily show. Okay. So now if I sit and compute the L3 norm of this, so each coordinate will give me a value at most this quantity. And how many coordinates are there? Something like X times Y.
Okay. Log mod X.
Yeah. So
like number of X.
Yeah. So actually maybe this should be
X times Y, because
X
this
times,
is
not
Y.
plus.
X times. Yeah.
So it should be this. So you plug it in, and this is what you get. Similarly for this, so here this is Px times Py. Okay. And
it should be the same. It should be the same kind of upper bound, right? Because this bound does not care what distribution you're working with. This bound is an absolute bound. It doesn't care what distribution you're working with.
No, but here it is the same probability distribution. So I think this requires some analysis, some thought. But anyway, I believe.
You're saying that in this.
Because it's Px times
that for the
Py.
second thing.
Yeah.
Right. The expectation is over Px times Py. Okay.
Yeah. Okay, but yeah, so I have to check it again. But okay, so let's for now believe that this is also true. So okay, yeah. So doing that, like the point is, I want to say how large T is. T is a property of the probability distributions, Pxy for sure, but one can give some sensible upper bounds, which look like the alphabet sizes, okay? Some like third power of alphabet sizes. And then this D becomes a mutual information, which is a minimum of log X or log Y. So I just want to show that this T is reasonable for many distributions of interest. Okay, but in any case, I mean, we'll not bother about T so much because it's a fixed property of the underlying probability distribution.
I think you'll be able to do it by maybe taking a Cauchy-Schwarz and then some concavity property of log, I think.
Yes, I believe so. Yeah, some concavity property will be there. Not
Yeah.
Cauchy-Schwarz, but I think just concavity property.
Okay, just yeah, maybe.
Just concavity. Yeah, so I'll actually have to work it out and do that. Someone missed it. Okay. So now let's see what we are going to do. Okay. So now, yeah, there was why this becomes X. Slides are a mess. Yeah. So but anyway, I mean, let's say we have these two probability distributions, Px and Qx. Now what I'm doing is I'm taking n IID samples from Px, from the probability distribution Px. So now my sample space is n tuples of X. So consider the centralized normalized random variable. So what is the random variable doing? It's a function. It's mapping this n tuple x1 to xn to this real number.
So this is just like what you get when you want to apply the central limit theorem, right? So you're forcing the central limit theorem to come in.
Yes, I'm forcing that. Yeah. So let's see what I'm doing. So okay, so these are n tuples of X, and remember I had the log likelihood ratio, right? So what was that? Which will map a sample point y in this case y to log of py by qy. Okay, so that's what I'm doing. So now I have n sample points. So this is the ith random variable. Okay, so which is mapping xi to log of pxi by qxi. Now I take a sample average over these random variables. Okay. So if I put in the independent probability distribution on x1 to xn, which I'm going to anyways do. Okay, so think of it, I'm taking n IID copies of the log likelihood ratio random variable. Okay? And I'm taking the sample average. This is the first sample average. Then I'm removing the expectation, okay, which we know is the relative entropy. Okay, so now the numerator, okay, is the sample average with the expectation removed. So that's the normalized adjective of it. Okay, so the numerator is the normalized sample average, and sorry, the numerator is the centralized sample average. Okay, centralized means I'm removing its expectation. Okay, so take the centralized sample average random variable, then normalize it. So normalizing it means that I want to drive down its standard deviation to 1. Okay. So what is the variance of the numerator random variable? So there's some centralization, but centralization
it's exactly n sigma square.
Yes. So the centralization does not change the variance. Now, these are independent random variables, so the variances will add up. Okay. So the total variance of the summation, okay, is
n sigma square, right? Where sigma square is the variance here.
Yeah, with sigma, I'm just wondering.
No. We need the root. We need the root for central limit theorem.
Yeah. But we need the root, but I'm wondering whether this n goes in the numerator or the denominator.
No, this is completely fine. This is absolutely perfect. What you have
No,
written.
no. This is the expression, I think, when I take the sum, but I don't take the sample average. Okay.
Oh.
I think that's the
So
case.
what is it? If you have x1, x2, xn, if you have x1, x2, xn IID, then x bar, which is the sample average, x bar minus mu divided by square root sigma. Oh, the square root n should not be there. I think the square root n should not be there.
I'll have to check that. Yeah.
Yeah. We have to check that.
N and
let me just check Wikipedia very fast. I mean, this thing is a little dicey. I know. I always make the same mistake. Let's say central limit theorem. Second. Wikipedia.
No, wait.
Okay, this is a little.
Yeah, I think it's not there. I mean, let me correct. I think the way to prove it is that I strike this out and I put an n out here.
Yeah. Yeah, this is perfectly correct, I think.
Yeah, I think this is the correct. Yeah. Okay.
So yeah, Wikipedia says that there's a multiplicative square root n term. So there's a square root n outside the summation also.
No.
Right, sorry. Okay.
Let me slow down. I think this is correct. No. So you take the sum random variable, remove its expectation, okay, and then divide by the variance of the sum random variable. That's it.
What is the variance of?
That is this.
That is this. Yeah. This is correct. Okay.
So this statement is correct. Okay.
Yeah.
So this is the centralized normalized random variable that we define, and by the central limit theorem, this centralized normalized random variable approaches the Gaussian random variable in measure. Okay, so this is the limit of random variables in measure, but we'll see in simple terms what it means.
It just means that the cumulative distribution functions come closer and closer, right?
Correct.
For every value of x.
For every value, that's what. Okay, so what is the random variable G? G is the Gaussian random variable with mean 0 and variance 1, which is defined by the probability density function. Okay, given out here. Okay, so the density at the real number x is given by this expression. Okay, so the traditional central limit theorem is just a limiting theorem. Okay, but we'll need a quantitative version called the Berry-Assigned theorem, which actually says, as you just said, that the cumulative distribution functions of C will approach the CDF of G, but Berry-Assigned theorem actually says for a certain value of n, how close is the CDF of C at a point x to the CDF of G at a point x. Okay. So to cut a long thing short, the Berry-Assigned theorem for our purposes says this. So I'm putting the IID probability distribution on x1 to xn according to P. Okay, so the probability under this IID distribution that random variable C is bigger than x, some real number x. Okay, so this is close to that of the Gaussian. Okay, so I can say less than or equal to the probability that the Gaussian is larger than x. Okay, so this is the CDF, or maybe 1 minus the CDF. Okay, plus an error term. And the Berry-Assigned says that the error term can be upper bounded by this term. So at the top, you will have basically the third moment of the random variable. Okay, and we further upper bounded. Okay, so this T is the third moment of this random variable. Okay, and we upper bounded by this quantity called T. Okay. So this is T. This is just a probability. This is just a
Pranab,
property.
Can you just go back to the E of T? So T is a constant with respect to n, right?
Yes. It's just a property of P and Q.
It's just a property of P, Pxy and Pxpy. Okay. In fact, just Px and Py.
Just Px and P, yeah. So this is T, a
Yes.
property of the two probability distributions P and Q. And then I have to divide by this quantity variance, okay, to the power 3 by 2. So this is also a property of P and Q. And the dependence on n comes out, the square root of it. Okay. So now, if somebody tells you the variation theorem, you can infer the central limit theorem. You just take the limit as n goes to infinity. So this shows that these two CDFs, I mean the CDF of C approaches the CDF of G. Okay. Any questions? So now let me yeah. So let's go back to this slide. So let us see what happens. Or maybe I should keep this open. It's best to keep this expression in there. Okay. So okay, so what I want is so I want this to be less than or equal to epsilon. So I want this to be less than or equal to epsilon. Okay. So what is this telling us? So let's ignore this for now. So this says that this Gaussian random variable, okay, the tail of the Gaussian should be less than or equal to epsilon. Okay.
No, why do I want it to be less than or equal to epsilon? That is not clear yet.
Okay. So that will become clear in a couple of minutes, and we'll connect to what we did last time. Okay. So then, so I will go back and then the whole picture.
But for now, we just want to put a bound on the tail.
Yeah. So I'm going to do it. So the aim is to put a bound on this tail problem. So I want the tail probability to be less than epsilon. Okay. So if I ignore this error term, okay, then that is as good as saying that put a tail bound on the Gaussian random variable. Okay. Now,
and that is very easy using very standard techniques.
Well, yes.
So there is this upper bound on the Gaussian tail, right? E power minus x square.
Right. There's an upper bound, e power minus x square by x or something.
By something that I don't remember. Exactly.
By x. Yeah.
Exactly.
Yeah. But I mean, we are not going to do that. We are going to write the exact expression. Okay. So basically, the Okay. So I mean, phi is the
CDF.
CDF.
Standard normal CDF.
Okay. Of G. Okay. So this means that if I take x to be
phi inverse epsilon. I see. That's where the phi inverse epsilon comes in. Okay.
Yeah. So if I take x to be phi inverse epsilon, okay, then the probability that Gaussian is larger than phi inverse epsilon by definition is less than epsilon. Okay. So we know what x to apply to the central limit theorem out here. Okay, that is phi inverse epsilon. Now, let us see what does this give us. So now, say, Okay. So now I'm going to look at the probability that C is greater than the way
C is the centralized variable, right?
Yeah, centralized normalized variable. So I'm
Right,
going to,
right.
ask probability C is greater than phi inverse. Actually, the way I've written it might be phi inverse of 1 minus epsilon, but doesn't matter. Okay. So I'm going to ask probability that C is larger than phi inverse epsilon. Okay. Yeah. So what do you mean by C is larger than phi inverse epsilon? This means that summation I n minus n minus n times
N times dpq.
dpq. So this is larger than square root n times
Times phi inverse epsilon.
this is
Right.
what I get, right? Yeah.
Yeah.
Okay.
And the point is that this happens with very low probability.
This happens with probability less than epsilon.
Probability less than epsilon. Exactly less than epsilon. Yeah.
Yeah. So I've ignored that error term. So that error term will basically
No, you can take large enough n, right? You will say that for large enough n, that error term is like another epsilon or something.
I can take large enough n, and that's it. I mean, like the right hand side of this greater than. Okay, so instead of requiring it to be greater than square root n times the divergence variance times phi inverse epsilon, it has to be this plus some other quantity coming from there. Now what does this? Okay, so I know that this is less than epsilon. Okay, so what does this mean? So this means that from. So what was the first distribution? It was n IID copies of P. So from this distribution, px1 dot pxn. Okay, drop n equals x1 to xn.
For which this is for the this lower bound is true. Yeah. So you just want to prune away epsilon.
Yeah, this is just a pruning.
Right.
X1. Cx1 into xn, what larger
C is greater than 5 inverse epsilon. Yeah.
Yeah. Okay. So no. How to add a new page? Ah, okay. Yeah.
Yeah.
Yeah. Okay. So far so good. So I just will drop this, and what do I know? I know that the okay. I know that how much mass I have dropped of the entropy. So
Epsilon.
yeah, yeah. So loss of mass, loss of mass is less than epsilon. Okay. So that's it. So the I have okay. So remember what I'm trying to analyze. So let's come to this Dmax. Yeah. So you were asking what is this got to do Dmax? So if I look at Dmax, epsilon. So it is p to the tensor power n.
And q to the tensor power.
Yeah.
Oh no, I can see it now. I can see it now. Bloody amazing.
Okay. So this is what I want to analyze. I want to analyze the IID limit of Dmax. Okay.
Right.
So
right.
So that's what I've done. So p to the tensor power n is nothing but this distribution. Okay.
Yeah.
And I have to prune it for Dmax. So I'll just prune these guys where the C random variable is larger.
So I just have a comment. So there are a couple of steps. The thing is that you say, okay, there is an optimizer, and that optimizer is something like P prime. But the prune distribution, let's call it P tilde. Okay. So P prime may not be same as P tilde.
But that will be even smaller. That's the advantage of work with Dmax.
That will be even smaller. Exactly. That will be even smaller. So Dmax epsilon is less than equal to this pruning that we get from P tilde. So now we are only going to work with P tilde. We are not going to worry about the optimizer.
Yeah. Yeah.
So then you will say that on the that's it. Yeah. On this subset,
you're done.
This is
you're done. So I'm giving you a prune probability distribution where the loss of mass is less than epsilon, and I'm looking at what is the largest ratio there. Okay. So the optimal pruning is better than this, but
is even smaller. Yeah.
So the largest ratio there will be even smaller. Okay, but that's fine. Inequality is like this, so it's less than or equal to. Okay, so whatever we have proved, so that is n times
n square root n times d.
D
n times dq plus some small of n terms.
Yeah, which you can write in fair amount of detail now. So let me just.
So there will be 1 square root n the year term. This square root minus square root n vpq.
Yeah. So this quantity, that the sum of the log likelihood ratio is actually the log likelihood ratio for the product distributions. Okay.
Yes.
E to the tensor power and Q to the tensor power. Okay.
Yeah.
And once I've pruned, I know that this is not too large. So this quantity is less than nd plus square root
nd plus square root n vpq for 5 inverse.
Yeah, plus some little error.
Little often, yeah. This is nice.
So you can see in the first order dependence, there is no epsilon. In the second order difference, we know exactly what, I mean, what is the dependence on epsilon. Okay. And then plus, so
plus small, some little off.
Yeah, even smaller. So Let us just say it is even little O of square.
So this little O of n hides the upper bound that the variation theorem gives.
Yeah,
us,
yeah,
right?
yeah. It hides the upper bound, but at least let us convince ourselves it is little O of square root of n. Where was the variation theorem?
That was in the slides.
Ah, that was in the slides. Okay, so let's go back to this. See. Okay, so
Shouldn't you save this for later? I mean, yeah, we know what it is.
Yeah, we know what. No, any. I mean, the slides that I'll put up will be cleaned up. So, yeah. Okay. So there was this term. So what did I
No,
get?
in
So
this in this term you had like you have to multiply all of these things with an n, and that's when you get the square root n multiple.
Well, I know the n is already here, right?
Wait,
remember what was this? I mean, this went away. There was this n.
Oh, yeah. Sure. Yeah.
So that was the correct expression. So
yes.
Yeah. So no, the question is what is x out here? See, overall now I want the probability that c is bigger than x is less than epsilon. So if this term was not there, I know x is exactly 5 inverse epsilon.
Yes.
But now x is still a little larger than that. Okay. So how much larger? I mean, that is because of this additional term. But yeah, but you can see that. Yeah.
So this is not even little of n then, right? This is like
no.
It's much smaller than that. Oh, we have to see that t, how the dependence.
Yeah. We have to see that.
Yeah, so, because actually this t is not constant. So the comment I had made earlier, this t is not constant, right? When you take the tensor power n, that will show up in the upper bound.
No, that doesn't show up in the t. This t is a constant, but yeah. So okay, so at least let us. Okay, let
no,
we'll do a
but
rough
we're
analysis.
Computing that.
No.
Okay.
Well, we are doing a rough analysis now, but yeah, you can do a more refined analysis. I mean, there are error terms which depend on x. Okay, in the very assaying. I mean, there are versions of very assaying theorem where the error term can be made to depend on x. So I think for the best dependence out there, we will need that. Okay, but let us see how far we can go with this. Okay? I mean, this is the simplest variation type of theorem. So let us say I take n to be larger than 1 by epsilon, 1 by epsilon square wave. Okay, and then there will be some constant. So let us say n is larger than some constant by epsilon square. Okay, so that constant is enough to kill this off. T by variance. Okay.
Yes.
Yeah.
T by VA. Yeah.
In fact, I think this is even less than 1 because of some older inequality. T by variance. Check that. Okay. So essentially, really 1 by epsilon square. I think is good enough. Okay. So anyway, I mean, so some constant by epsilon square. Yeah. So some constant by epsilon square surely works. And then okay, and then for large enough n, and then for large enough n means larger than 1 by epsilon square. I can use this. I can use the rough analysis that I did. Okay, so which one was?
That was in a previous slide. You discarded that.
Yeah. Whatever. Not safe. Oh. What the hell is happening? Why can't
I,
some
no,
external
just
problem?
just click on this thing. I think click on this, the file lake.
No, it's. I think this thing is stuck. Okay.
Oh man, then you will lose progress. Then you will.
No, but the actual writing has been saved correctly. I think.
Okay.
Yeah. I mean, in the PDF, I haven't written much. Any lot of corrections are made in the PDF.
Okay.
Yeah. So the writing is saved. I'm going to share it again. Yeah. You can see this, right? Okay. Yeah. So maybe for a rough thing, you can replace this epsilon by 2 or something. Okay. So I want the Gaussian to be larger than phi inverse of epsilon by 2. So the Gaussian will contribute epsilon by 2, and the error term of variation will contribute another epsilon by 2, and then
epsilon by 2.
Yeah.
Okay.
So for large enough, but actually, I mean, the best ones that are known work for all n. Okay. Yeah, so I suspect you'll have to use the variation theorem that depends on x. So there are variation theorem where the error term depends upon x.
So this thing that we proved, this is slightly weaker than what you had claimed for all block length sizes, that the all k's in the previous class. That is a very strong claim, right?
Well, yeah. Yes. So this is weaker simply because of the error term. I mean, if the error,
yes.
Yeah.
And there you had an equality. Here we have an upper bound.
Well, but the equality is an upper bound because it's little O of k, right?
Little. Oh yeah. Right. Sure.
So it's really an upper bound. Yeah.
Yes.
So advantage of working with Dmax is that we wanted upper bounds for the strong contrast. Okay. And this strategy naturally gives us an upper bound on Dmax. Yeah. So
no, I'm just wondering how one might get that statement for every. In fact, that is already there, right? I mean, you have already mentioned this. So if you use some finer versions of variation, then you can write exactly that statement.
Then you can write exactly that statement. I mean, then it will basically then we work for all n. Right now, it's only working for n.
Working for some large enough n where we bound it by epsilon by 2. But okay, sure.
Yeah. 1 upon epsilon square or something.
Yeah, maybe like you were saying that, that you might have to multiply that little O with us 10,000, but to take care of the smaller values for k. But that's fine.
Okay, that's fine.
Okay,
so
I see.
So basically, the variations that that are sensitive to x. Okay. But what do you do if x is very small? So then you have to put in some large constant so that basically they work for. I mean,
right.
All x or something. Yeah.
No, I got it.
Definitely, this little O of square root of n business does depend on epsilon and the properties of the probability distribution.
Yes.
Yeah, but at least, I mean, for now, we can say that if I take n large enough, I can get something like this. Okay. Larger than 1 by epsilon squared, then I can. Okay. So yeah, so that's about it. So we have shown that Dmax epsilon in the IID limit is less than this quantity. Okay.
Yeah.
And and then there are I mean, you can run the argument in the other directions, and then you can say greater than it will be ND, then it will be minus of this quantity, minus of the variance term. Okay?
So that's for the other tail. That's for the other tail of the Gaussian.
Yeah, that is the other tail of the Gaussian. Yes.
Okay.
Yeah.
That's why the negative range.
Yeah. Okay. So so now let's come back and tie up with what was done in the last lecture and see why.
I just have a quick question. So, I mean, I'm not entirely sure, but by replacing epsilon with 1 minus epsilon, using the same argument, not doing anything more, using the same argument, can we show that d min also goes to d1?
Actually, yes. Yeah.
Okay.
Yeah. In fact, I mean, if you replace epsilon by 1 minus epsilon, this phi inverse becomes a negative number. Okay.
Yes.
Yeah. I mean, phi at epsilon equal to half.
No.
Phi inverse of half is 0.
Yes, phi inverse of half is 0 for
Yeah.
So phi inverse is with respect to standard normal. So it's 0. Right. It's 0.
Yeah. I mean, our Gaussian is a standard thing, mean 0, variance 1.
Yes.
Okay. Yeah. So let's now go back and recap what we've done. So what we have shown after this is that at least for large enough, so let me for now, let's say for now, okay, and larger than square. If you do it, we have okay. So we have shown that d max epsilon is upper bounded by nd plus a square root n term, which we can write down precisely, and then some lower order terms, where the lower order terms, I mean, it is little of square root of n. But yeah, I mean, a more refined analysis, I think if you use the right variation theorems and all that, you can show that it's actually order log n.
Right.
Big O of log n, but the big O of log n, of course, will hide epsilon and will hide properties of real. Yeah. Okay. So this is what we get. So so how does this tie up with our strong converse that we did last time? So appreciate that. I think I stop share. Or first stop this sharing and then start the other one. Yeah. So what will we do? Let's come from here. Okay. So let's recall that any private coin encoding decoding strategy with rate r prime larger than this quantity. Okay. Yeah. So we'll give error bigger than 1 minus epsilon. So this is just coming from the weak converse. Okay. So this is a refined weak converse where I'm minimizing over qy. And then we are converting the d min into d max. Okay, because as we have seen, to be useful for later purposes. So any protocol with this rate will give error larger than 1 minus epsilon. So now we are going to analyze this like d max epsilon of pxy with respect to px times qy, and there's a max min out here. So max over the input distribution px, min over
qy.
Min over qy. Yeah, and then there was this business of the max min less than min max. Okay, and then, which is always true. And this was fantastic for us because once you have min over qy max over px, we can just make it max over an input symbol x. Okay, and
max over an input symbol x.
Yeah, and for that we exploited the data processing inequality, or rather the joint convexity of d epsilon max, like this. So after we had this, so far this was one shot. So after we do this one shot, we can apply to the asymptotic IID case. So now, of course, the rate that we're interested in will look like max, like this quantity, but arbitrary probability distribution on x to the n. Okay, then minimizing what qy to the n.
Yeah.
This is asymptotic IID case. Now, as you've just seen here, we can interchange min max, then fix the symbol x, and we get this. And then there was this further upper bound. So I will not take arbitrary probability distributions q on yn, but I'll fix
you take the products.
Yeah, I'll fix the distribution q on y. Okay, I'm only allowing minimization over a restricted family. Okay, and on y2 there, I'll put the tensor power probability distribution. Okay? So I'm only minimizing over distributions of this form, some qy to the tensor power. So less than or equal to continues to be an upper bound. And now, yeah, so this is a slight refinement. I mean, I put in more steps and made things clearer, which was not there last time. So that's what I'm showing. Okay, so let's analyze what this is. So, okay. So remember, like I have n tensor copies, but my alphabets are fixed. The base alphabet x and y are fixed. Okay. Yeah. So this n tuple x to the n, I can break up xn into bunches of a fixed set of symbols. Okay. And the particular symbol x occurs kx times. That's just a name I've given. So x occurs a certain number of times in xn, which I'm calling kx. So now let's analyze what this is. So let us look at the Preune probability distribution, the sub-distribution, which achieves d epsilon for this. Okay. So take the maximizing n tuple xn and look at the sub-distribution that achieves the achieves the optimization in d epsilon max. Okay, fine. So instead of doing this optimum thing, I'll do a suboptimum. And remember, because d max, if I do anything suboptimal, it will only get a bigger quantity. So that
it'll only blow up.
This is this is less than or equal to this blah blah. Okay. So what I'm going to do is,
how do you get the summation?
Yeah. So that's because this is tensor power.
You can break it up.
Yeah. So what is this?
You're breaking the x's up into blocks. Okay.
Yes. So what I'm doing is, let's concentrate on the maximizing xn out here. Okay. Okay. So fix this maximize xn, but I'll not take the optimizing sub-distribution out here. I'll do something which is slightly suboptimal, but for the same xn. Okay. So in this xn, symbol x occurs kx times. So look at the bunch for the fixed symbol x. Okay. And the probability distribution.
Oh, that's why you broke up the joint distribution into conditional distribution, so that you could turn this into a summation.
Yes. Yes. So So what is happening is, look at the bunch corresponding to the fixed symbol x. So now this will be p of y given x to the tensor power kx. Okay. And correspondingly on those coordinates at qy to the tensor power kx. Okay.
But shouldn't this be equality then?
No, it's not equality. So you'll realize in a moment why. So what I do is, let me find the optimizing sub-distribution for this d max. Okay, but now my error parameter is not epsilon. My smoothing parameter for d max, I will take epsilon over x. Remember, mod x is a fixed quantity. Okay. So what is this? So what is this telling me? Take the optimizing sub-distribution for the symbol x, for just that bunch. So that achieves some log likelihood ratio, which is captured by this quantity, and that loses some mass. How much mass does it lose? It loses mass epsilon by mod x. Okay. So this I'll do for every symbol, and then
that's why
stick the
mod x. Okay.
Yeah, and then take the product probability sub-distribution. So I will just tensor all these sub-distributions together to get a sub-distribution for n copies. Okay. So that by triangle inequality will lose mass at most epsilon if I do that.
Yeah.
Okay. And the log likelihood ratio that will give is the summation of the log likelihood.
Oh, I see. That's why the inequality is there, because this sub-distribution that you have come up with, it may not be the optimal, but it will give you an upper bound. I see.
It will give an upper bound. Okay. So again, so less than or equal to this. Yeah. So then what I'm doing is
then we can use whatever we did today, right? Once you have this form, once you have the tensor form, this very nice form, you can simply take the kx out for large enough kx, for large enough n, and that's it. You're done.
Yeah. So 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 let's say, okay, so I cannot say that all the kx's are large, but let us say I have the more refined version which works for all kx, okay,
Which works
for
for
as
all
many
kx's,
copies.
yeah.
Yeah. Okay. So
Yes,
then
yes.
I can
So we
write this
need
up.
that. We need that. That is
We need that.
that
Yeah.
stronger version is important.
Yeah. We need it at least for this. Yeah. Definitely. So yeah. So when I correct the slides, I will fix that. I'll show how to get the stronger version. Okay. So assuming the stronger version, we can write this expression, and then that's it. We are done. So min
It's
over
not
qi.
x0, right? It's py given x.
Yeah, x. Yeah, this x0 is from I think the previous slide. Yeah. So this should
From
be
previous thing,
given
yeah.
x. Yeah. And then okay, summation over x, but now I'll replace it by the maximizing x. Okay. The x that achieves the maximization, but now this is a single letter maximization. Okay. So a further upper bound, and then factor of n will come out, of course. Okay. And then it's O epsilon of kx, but the summation of kx is there. So it's O epsilon. Okay. That's it.
Okay.
Yeah. So that
And then, I mean,
basically,
inside the expression for d, you can simply multiply and divide by px, and that's it. That's the proof.
well, yeah, there was more. So yeah, so just let's recall how the proof is. So this finishes the proof of this, where we have brought in today's lecture. Okay. I mean, assume it works
Oh, you
for all.
can't do that because there's a max over x. Okay.
What max?
No, max
So
over x, I'm saying. There's a max over.
yeah. That is there because I'm further upper bounding.
Yeah.
Yeah, I mean for different x's, this Shannon relative entropy will take different values. I say that okay, forget it, upper bounded by optimizing over this x also.
Right.
So that's it. So that part is fine. So now, what have I proved? I proved that my strong converse rate, which started out by looking like this, max over input distribution P, but on Xn, minimizing over distributions Q, but on Yn. Okay, this d epsilon max quantity. Okay, so this turns out to be less than n times the minimization over Qy, but this is over a single letter minimization. Then max over symbol X, but this is again a single letter maximization of this quantity. Okay, plus little o. And then we said, okay, let us analyze what is this min over qi max over the symbol x. Okay, and it turned out to be equal to the maximum mutual information between x and y when I'm maximizing on input distributions.
Right.
So how was that? I mean, you start off with this. Then the first observation is that the mutual information where I'm taking the Shannon relative entropy between joint distribution pxy. Yeah.
You can minimize this when qy equal to py. That's the first step.
Right? That's the first step. Yeah. So that you can prove by concave logarithm that the minimization is obtained when qy is equal to py. So you apply
then by the minimax theorem, you can switch the min max.
Yeah.
So the qy goes outside.
Yeah.
And then
the
why
same
is this
argument.
Equality? Why is this
equality? The same argument as before, that joint convexity of Shannon relative entropy. So express the joint distribution as a convex combination of like single point distribution on X.
Conditional distribution. Yeah. Okay.
Yeah. So which we did earlier, right?
Yeah.
That is this one.
That. Right.
So this you repeat for D. Okay, so you get this, and so this finally finishes. The strong converse rate is less than n times the channel capacity plus little o.
Some small little off, and yeah. Okay. Got it.
And of course, achievability was easy because, like, I mean, for achievability, I could have maximized towards input distributions on Xn, but I choose to do something weaker. I'll only do a single letter maximization and then apply it on P to the tensor power n. Okay? And
that's good
then,
enough.
Yeah, that's good.
Okay.
Yeah. So here, so here also one will have to use the second order asymptotics, but yeah. So whatever you can do for the D max epsilon, you can do for D min epsilon. You can lower bound for D min epsilon. Okay? But it's essentially related to changing epsilon to 1 minus epsilon.
Right.
So again, you cannot really work with D min. You have to work with smooth
Dmax.
D0. Yeah, no. I mean, if you want to work with, you can work with Dmax 1 minus. Correct. That's correct.
Okay.
Yeah, and that's about it. So we will stop the lecture.
Baba. Baba. Hello. I'm Rector.
Yeah. Okay. So any questions?
No, I'm fine.
We are supposed to go now.
Okay, so I'll stop the recording. And we'll meet next. I'll have to really update the slides.